so let's talk about torque. All right, so we define torque as, and this is the symbol for torque, looks like a little T, as the function of the distance, the radius, times the force, where the force has to be perpendicular to that radius, okay? And we'll talk about what this refers to in a second, all right? So here's an example, very simple example, okay? So let's take a look at this one over here. Okay, so here we have, this could be like a wrench or something. So here's my pivot point. The R is 1. R is 1 meter. The force is 50 newtons. So what's my torque? Okay, so just R times F. Now the formula is R times F sine theta. But what would this angle be? That's 90. And what's the sine of 90? 1. So that's going to be 1 times 50 times 1. Now the radius is in meters. So let's look at the unit, okay? So it's going to be meters times a newton. So the answer in this case will be 50 newton meter. Okay? It's 50 newton meters. Which, by the way, would be equivalent of, because the number of newton is what? A kilogram meter per second squared. So it will be the same as kilogram meter squared per second squared. Or kilogram meter per second squared. Okay. So far so good, right? Easy? So there you go. So let's take a look at another example. But this time we'll have an angle. Hold on. Okay, so let's look at another example, but this time we'll look at an example where the force is being applied on an angle, okay? So let's imagine we have some sort of a lever. So here's my pivot point. Let's say R is, let's say it's 10 meters. And let's say my angle is 30 degrees. And I'm applying a downwards force, let's say of 10 newtons. Okay? 10 newtons. Well, it's my torque in this case. So my torque is R times F times sine theta. Now, in this case, we want, so you got to be careful, right? You got to understand what the sine theta refers to. It refers to that perpendicular component. So, like, don't just start plugging numbers in, because if I gave you, imagine I gave you this angle. Because what would this angle be? Be 60, right? And if you weren't paying attention, if I give you that angle, you might say R times F times sine 60, and you wouldn't get the right answer, because what would that component give you? Yeah, it would give you this component. And we don't want that. We want the component that's perpendicular to R, okay? So don't just blindly plug in numbers. You have to understand what that sine theta is referring to. Okay, so in this case, the torque is going to be the radius, 10, times the force, which is 10, times the sine of 30, which is this component over here, which for some reason I have it pointing up. It's actually pointing down, which we know is 0.5. So this should be 100 times 0.5, which is 50 Newton meter. Okay, so far so good. Easy enough. There's I'm trying to remember the name of the, was it Archimedes that said if you had a lever long enough, it can move the earth? So how many of you ever try to move something really heavy using torque? That's the concept, right? If you want to move a really heavy object, the longer the lever, the more force you can generate, right? So next time, you know, if to lift something really heavy, think about torque. Or if you want to change, I know Maury does this, where you're changing a tire. The longer the rod that you're using to loosen the bolts, the more torque you generate. Okay. Anyways, all right. So torque has some very practical applications. including diving boards. Next time you're on a diving board, we're going to think about torque, okay? So let's imagine you're on a diving board. So you're right here. So, whoa, what's going on? Okay. So let's imagine you're on this diving board. This is you. And you have a mass of, let's say, 100 kilograms. Okay? We want to know what is, we're going to call this F1, and we're going to call this F2. Imagine we want to figure out what F1 and F2 are. And we're going to say the board has no mass, okay? Just to keep it simple today. So the board, no mass. We'll talk about when the board has mass tomorrow. Alright? So the board has no mass. We're going to figure out using torque. Now, we've looked at force, right? You guys know that if something is not moving, then we know that the net force is what? Okay, net force is 0, right? But here's the thing. We're going to use torque also now to figure out force. Because if something isn't rotating, we can also say that there is no net torque. Okay? And we're going to use those two concepts to figure out what is the force at these 2 points in the diving board. Okay? So we understand that if there's no net force, there's no what? No acceleration. Here's the thing. If torque causes rotation, if there's no net torque, either the object is going to continue to rotate at a constant rate, or there will be no rotating if the object is stationary. So right now this diving board isn't rotating, so if there's no net torque, it's not going to rotate. What would happen if it snapped right here? Imagine the diving board snapped. This connection that's holding down the diving board snapped. What would happen to the diving board? What could happen? Which way would it rotate? Yeah, it would rotate this way, right? Right? It would rotate this way. So actually, let's try to figure out which way F1 and F2 are pointing. So I'm going to pause this for a second. I'm going to come back to this, all right? Okay, so we looked at what it actually looks like using a ruler and a weight. So what we noticed is that F2 is actually pointing up, and F1 is actually pointing down in this scenario, okay? So when you come across questions like this, you're going to have to try to visualize which way the force is pointing. Sometimes it might not be so obvious, so you're going to have to like think about it and maybe draw a picture or something like that so you can visualize it. Okay, so all right, let's work this out. Here's the thing. We know that the net force is 0. Okay? So that means if we look at the net force, we know it's 0, and it has to be the sum of what? Oh, and which way would there's a third force here, right? It would be the what? The weight.
So are you recording?
Yeah. I hope I'm recording. Am I recording?
I don't know.
Let's double check. I'm recording. Okay. So it would make sense that the weight and F1 have to equal what? F2, right? So we could say the weight and F1. Now I'll just make those two positive, okay? Is equal to F2. So we can say this. We can say FG plus F1 minus F2 is 0. Does that make sense? But you'll notice the problem here, right? We have two unknowns. We don't have F1 and we don't have F2. But we have some other piece of information. We know that it's not rotating. Okay? We know it's not rotating. So let's think about this. We know that torque is force times the radius, correct? Okay. Now there's three forces here. So we have this force, which is mg. Oh, I didn't give you the distance. Sorry, I apologize. Let's say this is 2 meters, and let's say that this is from here to here. Let's say from here to here is 4 meters. Okay. So the diving board is 6 meters long. From F2 to the end of the diving board is 2 meters. From the person to the end of the diving board is 6 meters. Now, what you do when you have a question with torque is you look at a pivot point. You have to have a pivot point, a point at which you have a rotation, okay? And you could pick. Here we can actually pick 2 pivot points. I could say maybe my pivot point, because if you think about it, you could get rotation at this point, but you can also get rotation at this point. So we have actually 2 pivot points, but you just pick one. So I'm going to pick this as my pivot point, okay? Because if you look, you have to know what your distance is to the pivot point. So you need a pivot point, a point at which the thing will rotate, okay? So if we pick this as our pivot point, you'll notice something. We know that the net torque is going to add up to 0. Okay? And that's going to be the sum of, well, let's think about this. This force is being applied downwards. And here's my pivot point, which is how far away? 6 meters. So if we say that the weight of the person times 6, that could be one torque, right? We've got a force over a distance. And that will cause my diving board to rotate this way, correct? Now this force is would cause the diving board to rotate which way? It would be the opposite. So if I make clockwise one sign, like positive, then that has to be negative, okay? So we'll say minus F2 times the distance to the pivot point. Now how far away from the pivot point is F2? It's 2, right? So times 2. And then we have the third force, because there's a third force. But you'll notice something. F1 is right at the pivot point. So that would be, Laura, it would be 0. So guess what? We don't need to worry about F1, because it's 0. Okay? We okay with that? That's why you pick a pivot point, because that way you can eliminate one of your torques. Now you'll notice something. We know what Fg is, right? We now can say that Fg times 6 is equal to F2 times 2. We can make this easier and say Fg times 3 is equal to F2. Now Fg is what? It's 100 times 9.8 times 3 is equal to F2. Okay, so what's my F2? 240. No? That's okay. It's alright. 2,940. Okay? Newton meter. Alright, now we have F2. So now what you can do now is you can go back to this equation over here, right? Which is what your net force equation. And we know what F2 is. So now we could say, well, let's solve for F1. So F1 would be what? It would be, bring the F2 over would be positive. It would be F2 minus Fg. So F1 would be F2, which is 2,940 minus Fg, which is 100 times 9.8, which is 980. So 1,960 Newton meter. Okay? So that's just a very simple, very brief introduction to torque and how you could use it to solve static scenarios. Static scenarios, again, are things where there is no what? There's no acceleration. And in this case, there's no acceleration up, down, left, right, or there's no rotational acceleration. Okay? And then tomorrow we'll look at some more complicated scenarios. Alright, ladies? That is it.